Hi, my name is Bo. I am a first-year PhD student from Duke University in the Department of Mechanical Engineering and Material Science. Today, I am giving a presentation on the influence of material properties and fracture properties on crack nucleation and growth in thin film. First, let me introduce the background. Think of a film deposited at high temperature and then cooled down, or wet soil undergoing drying. The films are assumed to be subjected to a bi-axial state of stress that arises due to a mismatch in the material properties between layers. When the top layer is overstressed, cracks nucleate and propagate. We're interested in the sensitivity of crack patterns to variations in model parameters responsible for both nucleation and growth. Previously, as shown in the red figure, we have examined the influence of spatially varied fracture toughness and critical fracture energy on the thin film desiccation with cohesive model. In the cohesive model, strength of the material enters the governing equation in the energetic form. To employ the material strength itself as a control factor of nucleation, we adopted the nucleation model, which I will introduce later. To study this type of cracking of thin film, a two-dimensional shear-like model was adopted. An elastic thin film is bonded to an elastic thick layer above a rigid substrate. The film is under uniform biaxial stress. Only the top layer will fracture. The total energy of the system consists of the external energy, the degraded elastic energy, the degraded interface energy, and the approximated fracture energy. In our simulation, we increase the eigenstress in the same rate as time. Periodic boundary condition is applied so that the result of a small piece can be put together to form a large picture. We generated the random fields of the material properties by using k-out expansion. Start from periodic exponential correlation function with two kernels to choose, the exponential kernel and the square exponential kernel. The effect of different kernels will be shown later. Then we solve the eigenproblem of the analytical correlation function. Use the eigenpairs and generated Gaussian random variables to put together a k-out expansion as the underlying Gaussian field. And since this field is unbounded, we need one more step of mapping it to gamma field. It is bounded, and it is where we control the mean and the variation of the random fields for our simulation. The two random fields can be designed to correlate with each other, but so far my results were from homogeneous fracture toughness and the random field for the strength. Here are example random fields for different kernels and correlation length. The square exponential kernel produces smoother fields compared to the exponential kernel, and smaller correlation length produces more peaks and valleys. Now, let me introduce the nucleation model. There are three scenarios for brittle material to fracture. First is from the bulk material, which is controlled by the strain surface. Second is from large pre-existing crack, which is controlled by the Griffiths competition between the material bulk elastic energy and the surface fracture energy. Third is from boundary and small pre-existing crack, which is controlled by the two factors above combined. For stress envelope, we have existed model, the Drucker-Prager model. It is a function of the stress tensor invariant. Its shape is controlled by the tensile and compressive strengths. We base our work on the recent developed nucleation model for phase field fracture from Aditya Kumar and Oscar Lopez-Pamis at the University of Illinois. The way this model employs stress envelope is by adding an extra term in the governing equation of fracture. It is a function of the degraded Cauchy stress invariant. The shape of this envelope will approach to the Drucker-Prager envelope as we reduce the regularization length. One point to be noticed here is this numerical parameter delta that we need to calibrate for any set of material property and mesh spacing. We calibrate the delta by matching the J integral to the value of prescribed GC during static crack propagation. Apply serving boundary condition to a stripe with initial edge crack. Compute the J integral over the four boundaries. Tune the J integral to the value of GC by changing delta. In this model, damage is irreversible only after material is close to fully damaged. This particular irreversibility constraint, together with delta, lead to a different effective regularization length for damage initiation and propagation, scaled by square root of 1 plus delta. You can see that in the middle figure over here, a bubble for damage initiation. And from there, we know that delta has to be greater than -1. The upper bound of delta is limited by the mesh size. We do want the effective regularization length, usually scaled to be smaller than the prescribed one, to be adequately resolved by the mesh. Here's an example of the J-integral curves for different delta values. The plateau of 0 delta and how sensitive the plateau is to a change in delta are different for different set of material properties and mesh size. But the general picture is that the J integral value at steady propagation increases as delta increases. And here, if I chose a delta value greater than 2.86, the J integral will end up being greater than 1. The J integral over GC will end up being greater than 1. For a change in tensile strength, samples of delta were calibrated from sample points of tensile strength. Fit the delta values by a smooth, continuous function. Here's an example of tensile strength field and the corresponding delta field. And this is the first time this nucleation model is implemented with spatially variant material properties. This is the new contribution from this work. Without loss of generality, here are the two governing equations for mechanical and fracture subproblem, respectively. We chose quadratic degradation function, and in our phase P model, d equals 0 means the material is intact, and 1 means the material is fully damaged. D is irreversible only after it reaches to 0.95, as required by the nucleation model. The system was approximated in standard Fala-Ammon method with Galerkin discretization, and then solved by a staggered scheme. And for each new time step, we first fix the damage field and solve for a displacement field in the mechanical subproblem, and then fix the displacement field and solve for a damage field in the fracture subproblem. The loop keeps going until both fields gives a satisfied residual in the mechanical subproblem. For the result, first, a short recap on the cohesive result from previous paper. The fragment size for the square exponential kernel increased with increasing correlation length. There is no obvious fragment size change for the exponential kernel. Crack path showed more dependence on the distribution of fracture toughness than critical fracture energy for the square exponential kernel. Crack propagated and pattern formed progressively. Fragment orientation tended to align with the x and y axis as correlation length increased. And for the nucleation model result I have so far, there is no obvious sensitivity of crack size, of fragment size, or orientation of correlation length or kernel type. We do see that joints of the crack path tend to form at centers of the highland of the tensile strength, and crack patterns formed rapidly. We wanted to compare the damage evolution of both models from the same random field of tensor strength and the corresponding critical fracture energy. I have tried my best to make two simulations apples to apples. For a plus minus 10% variation in the tensor strength field, the corresponding critical fracture energy field will be of plus minus 21%. Here are snapshots for damage evolution with random fields, critical fracture energy, and tensor strength of the same distribution for two models. The top row is for the cohesive model and the bottom is for nucleation model. The first column is the damage initiation. Both started from weak materials. The second column is the time just before damage localization. The rest two columns are the time of the first crack appearance and final time of simulation with cracks superimposed over critical fracture energy field or tensile strength field. Nucleation model localized earlier than the cohesive model, and it localized rapidly. Keep increasing the loading after the first localization only added a few more cracks on the nucleation result. Fragments of nucleation results are mostly in polygon with 5 or more sides, while cohesive results are mostly rectangular and polygon with more sides but still close to the shape of rectangle. The damage evolution before localization for cohesive result largely revealed the resulted crack pattern. And for the nucleation model, although places with high damage before localization resulted in crack, we cannot see a strong indication of crack pattern before localization. To quantify the influence of the tensile strength or critical fracture energy on the damage field, we use Pearson correlation. It represents a linear relationship between the two variables. And when p equals to 1, it means we have a positive correlation and that damage tends to be higher near the peaks of tensile strength field. P equals to minus 1 means we have a negative correlation and that damage tends to be higher near the values of tensile strength field. P equals to 0 means there is no linear correlation. Here are the plots for the correlation coefficient over time. The first sample point on each curve is the frame of damage initiation. The pairs of frame before and after damage localization are those indicating an abrupt vertical decrease. Cohesive model showed a gradual shift from strong negative correlation to weak positive correlation, and then slowly dropped to almost no correlation before damage localization. Nucleation model showed a fast increase to strong positive correlation and stayed on the plateau till localization. After localization, both models have slight change in correlation but stayed in the weak to no correlation zone. And so far, there is no obvious sensitivity to random field parameters other than the localization time for different correlation lengths from the square exponential kernel. And while the two different models clearly show different behavior, it is not clear which one is closer to what is seen in actual experiment. In future, we will look to understand more details of thin film fracture experiment. That is all I have for today. Thanks to all the organizers and participants for your attention. I look forward to questions in the Q&A session or by email.